Hey guys, hope everyone is doing fine. So in this video, I will show you how to run a case over your custom built OpenFOAM solver. So in the previous video, we looked at how you can develop your own OpenFOAM solver. So if you have not watched that already, then I suggest that you do it first. So I'll select a version of OpenFOAM that I have in my system. After that, let's go to the foam run directory. Inside this, okay, so now I am inside the solver that we made in our previous video. So the name of the solver was new icoFoam. We changed some things inside. We added the temperature equation and made our new solver. So let me show you how does this look like. So what we did was we added the temperature equation, right? This part. So what I have changed from our previous video is, so I have added this, I have put this correct boundary conditions for temperature after solving for temperature equations. And also previously this part was inside this loop somewhere here. So at that point, every time when the pressure was being updated, the temperature equation was also being solved, but it's not necessary. So you can take it out and put it after this piso loop, after this loop. So besides that, everything is same. So now we need to compile. First, let's clean the previous builds and compile with make. And yeah, it's compiled and the location of executable can be found by this last line. So you can go to this location and you can find your solver there. Another way to check is just type new, the name of the solver, ico, and press tab. It should itself complete the line. So this up to this point we have already looked at in previous video. After this we will copy a case from icoFoam, a tutorial case, and then change it, add something, and run that case over this new solver that we have built. So let's do that. So I will go inside foam tutorials. Inside this, you can find all the tutorials that are already present when you install OpenFOAM. I will be going inside incompressible, icoFoam. In icoFoam, you have cavity and elbow, two cases. If you go inside cavity, there are still three different cases: cavity, cavity clipped, and cavity grade. So I'll copy this one, cavity, and paste it inside our foam running directory. To copy this, you need to have another command, cp -r. This is for recursive copying. This is what I copied just now. So let me move this inside this folder. So this is the solver and this is the case that I just copied. So let me move inside that. Now inside any case in OpenFOAM, you would have these, at least these three folders: 0, constant, and system. Now, yeah, let's look at this one by one. Now let's go inside the 0 directory. There are two files inside 0 directory, pressure and velocity. Now this makes sense because we copied this case, which is the cavity case, from incompressible foam solver, and it does not need any other fields besides pressure and velocity. But while making our own solver, we added the temperature equation. So we need to specify the initial conditions and boundary conditions for this temperature field inside the 0 directory. So to make a temperature field, just copy one of those files, either pressure or velocity. I would copy the pressure for now and name it as temperature T. So now you have pressure, temperature, and velocity. But since you just copied the pressure file and named it a temperature, you need to change the dimensions and other stuff. So let's do that. The first thing you need to do is, so the name of the object is not P, it's T now. And the dimensions should also be corrected. So the dimensions should be of Kelvin, which is like this, mass, length, time, and this is temperature. So it's 1. Internal field uniform list to 300 kelvins. Okay, I think I need to explain the case first. So what's the case that we are solving? Okay, if you search WIKI add temperature to icoFoam, yeah, you can go to this link, which describes how you can add the temperature, and also yeah, explains how you can run your own case after building your own solver. So this is the case that we are trying to simulate, which is the cavity case. And so all these 3 walls are fixed, while the top wall is moving at a specified velocity in x direction. And this is a 2D simulation. So this is the case that we just copied. So the temperature should be a fixed value. And you have to specify the value, which is going to be uniform 350 kelvins for now. And other fixed walls also have a fixed value of temperature. Only the top wall has 350 kelvins. Other than that, every location has 300 kelvins. But OpenFOAM inherently has a 3-dimensional setup, so you need to specify that what we are doing is a 2-dimensional simulation. So how you do that is you specify the front and back planes as empty. Okay, now let's also look at the velocity file. And so all the field is specified as 0 meters per second. The top wall, moving wall, is specified as 1 meters per second. So it seems like it's okay. So after working on this 0 directory, let's move to constant folder. Inside constant folder, you just have one file, transport properties. Now let's check that out. So in transfer properties, it already has a parameter called new. Now this is a diffusion coefficient for momentum, but since we added a new equation, temperature, and the diffusivity of that field is dt as we have coded in our solver. So this should be specified in here. Now the dimensions should also match, but since the temperature is what being affected by the velocity field, the units of both of these should be meters squared per second, which is already correct. So we can just change the values as required here to run the simulation. So for now, I would do this 0.002. And after this, let's move to system folder. Inside system folder, we have 4 files. Block mesh dict is just the dictionary file which is used for making the mesh. We'll look at this control directory dictionary file at last, but first let's look at FV schemes. So inside FV schemes, finite volume schemes, you specify the schemes that you are going to be using for different components of the governing equation. So inside governing equation, you have a divergence of velocity multiplied by the mass flux, so which is already present here. But since we added the temperature, the divergence of temperature part should also be specified here because by default there is no scheme provided. So again, if we go to the solver, the source file of the solver itself, then you have this component. The temperature field is being advected with by the velocity field. So you need to specify what scheme you're going to use to solve for this component. So that can be specified in FV schemes. So I will do it right now. Copy. So the name should match from the solver. So it would be T, and let's leave the scheme as it is. Besides this, in the solver, you have this new component. So this, for Laplacian schemes, there's a default scheme already provided. So you do not need to add anything new here. So just save this. Now let's look at FV solution. So in solution, you provide the details of the solver for individual variables. Pressure and velocity are already specified because in this case, the solver already had those variables, but we have a temperature which is a new variable, so we need to specify what we will use to solve for temperature. So for temperature, I could just copied this from velocity field. So in temperature, the solver I want to use would be, okay, let's try the same solver as the pressure one and see whether it works or not. Okay, now you have to specify some preconditioner depending on what the solver you will be using. And the tolerance, let's decrease it even more. And the relative tolerance should be 0. So save this. After this, only thing remaining to look at is control dict. Okay, let's look at that. Inside control dict, you have the name of the application that you will be using to solve. So this name does not affect which solver you will be using. It does not throw any error if you just put a random name over here. So start time. So let's just check the end time because we will be comparing our results for this time period. So other than that, everything looks fine. So save it. So it seems like our case is ready to be run. To run the case, you need to be inside this directory where you can see these 3 files directly. So let's create a mesh. To create a mesh, you do block mesh. Okay, the mesh is created. You can also check the mesh by typing check mesh, which gives you different parameters associated with the mesh that's generated. These parameters, maximum skewness, these factors are important when you have a complicated geometry, but for our case, it's a simple geometry and it says meshes. Okay, so we can move forward. Now you can run your case over the solver by typing the name of our new solver. Now, if you do that, it again gives some error. It says unknown asymmetric matrix solver PCG. So while solving, so it says the error is here. fp solution solvers.d. So it did not, so only these were the possibilities. But instead of this, we used some different solver. So we need to change that. Let's do that. System fp solution. So we should choose one of these. Okay, let's choose PBICZ. P, is it like this? Yeah, and save it. So while changing these files, you are just changing the files in the case. So you are not changing anything for the solver. So you do not need to recompile the solver. Now, after changing the case, let's try to run it once more. If it throws an error, if it throws, then we'll see. Okay, it says the preconditioner is not working. That, I mean, the preconditioner that we specified is not even valid. So let's choose this one, DILU. So the preconditioner, DIL, save. Now it should run. Okay, it ran. And to check if our new solver solved for the temperature equation or not, you can look at what variables it is solving for, and it shows that there is temperature. So it did indeed solve for the temperature. Now after this, if we look at the folder inside, there are new directories, time directories that are being created here. And another way to look at the results would be to visualize this. We can use ParaView to ParaFoam to visualize our results. Let's do that also. And after it is open, just select the properties that you want to load. You do not need this, just and press apply. So the temperature. Okay, so this is the initial temperature field that we provided. So these are the initial conditions. At 0 time, we have the upper boundary of temperature specified to be 350 kelvins. It is correct. And other than that, everything is 300 kelvins. Now let's look at velocity field. Initially, yeah, the same thing. Velocity of 1 meters per second in the moving wall, and everything is at rest. Now let's go to the last time period, and let's look at the temperature field. This is the temperature field that we get. Now let me change the color schemes so that it's easy to compare with that WIKI. Okay, on the right, this is the case that we solved from our simulations, and in the left is the reference. If you look at it, then the temperature distribution after or temperature distribution at 0.5 unit of times is shown in both the cases, and both the cases show somewhat similar temperature field. So this shows that after adding the temperature part, the results from solver are matching pretty well. Now, what you can do is you can also visualize the velocity field. So the velocity, since the upper plate is moving in x direction, so the velocity should have a circular pattern going on there. So we can check if that's the case or not. Uh, okay, so to do that, you can make a glyph visualization, this one, and specify the velocity vector field. So this is the velocity profile that we have, which is circular in nature. So yeah, we did calculate the temperature at friction with the provided velocity and also visualized the velocity contour surf streamlines. So in this way, you can build your own solver and make new test cases to run over it. So this concludes this video, and thank you for your attention. Yeah, see you.